All right, let's look at some of the homework problems in 17.6. Let's look at number 2. We have R equal this. And we have to identify the surface. So let me rewrite this as like this. And let me talk about, before I go on, the vector equation of a plane. Through a point P0 containing two vectors A and B that are not parallel. Okay, so I have this point P0, and let's put A there and B here, and take another point in the plane. So P0, P, we can write as some scalar times A, so make A longer in this case, and some scalar times B, so we have this, and we can write it as, it as the sum of PA times TB. So actually, let's let A be there and B be here. T and S are scalars. So R, let's let that be the position vector of P. So that's equal to OP is, okay, let's let the origin be here. It's going to be OP0 plus P0P. And that's the position vector R0 plus TA plus SB. That's the position vector of P0. So if you look, that's what we have here. Here we have this being the point, and here we have scalars times two vectors. So that right there is the equation of the plane through the point 1, 0, 2, containing the vectors 2, negative 1, 4, and 0, 3, 5. Okay, let's look at number 6. Okay, we're going to use Maple to do that. We're going to do plot 3D x, y, z, u equal the range, and v equal its range. All right, so let's get Maple started. we'll do with plots. Plot 3D u plus v u goes from -1 to 1, and v goes from -1 to 1. Okay, so that's a good picture. Now, let's go back and talk about letting u be constant. Then we get u equal to we get y equal u0 squared. And so x and z vary, we get parabolas parallel to the xz plane. And when v is constant, we get z equal v0 squared. So we get parabolas, x and y vary, so we get parabolas parallel to the xy plane. So if we go back and look at Maple, follow the arrow, these are the parabolas when u is constant, the vertical parabolas, and the ones laying flat, they go around, follow the arrow. Those are when v is constant. Those are parallel to the xy plane. So we get these parabolas when v is constant. We get these parabolas when u is constant. And those are the grid curves. Okay, let's do the same thing with number 8. In number 8, I'm going to take and plot 3D cosine u times sine v, sine u times sine v, and cosine v plus ln of tangent v over 2 u is 0 to 2 pi, v is 0.1 to 6.2. Okay, and so we have this shape here. You can see through the middle of it. And let's go back and do some work. When u is constant, we get the vertical grid curves. So let me go back to Maple. And if you can see my arrow, we get these right here. The vertical, the ones that go up and down. So they look like half parabolas, one, or hyperbolas actually. So these are the when u is constant. When v is constant, we get cosine u sine v0, sine u sine v0, cosine v0 plus ln tangent v0 over 2. So here we get x squared plus y squared equals sine squared v0. Those are circles with radius sine of v0. And z's constant, so they're in the z-plane. So those are the horizontal grid curves. You can see their circles. Let's go back again to Maple. See their circles right here. If we move this around, you can see the circles, and those are when v is constant. So that describes the grid curves. Okay, let's go back. Let's look at 18. The lower half of the ellipsoid okay, we're going to take the minus since it's the lower half. And so parametric equations that describe this, we could just say x is x, y is y, and z is the square root, negative square root 1 minus 2x squared minus 4y squared. Now there's other ways you could do this, but that's probably the easiest. 20. So that says x is greater than or equal to 0. Let's solve this one for x. This is easier. So we can let x be that, then we can let y be y, and z be z. And since x is greater than or equal to 0, y squared minus 2z squared has to be less than or equal to 4. Let's see. So r of xy, you can write it as this. That's it. Okay, 22. We have a sphere. Okay, since this is a sphere, let's try spherical coordinates. So right here we have rho squared equals 16. That says rho is 4. X is rho cosine sine phi cosine theta. Okay, then we have z between -2 and 2. So z equal -2 means cosine of phi is -1/2. So phi is 2 pi over 3. And when z is 2, phi is pi over 3. So our phi's are bounded by pi over 3 and 2 pi over 3. And our theta's bounded by 0 and 2 pi. So we have our parametric equations to be this. There's no restriction on theta. Alright, that's all we needed to do is find parametric representations. Okay, 28. We're going to use maple. This is a surface of revolution. X is 4y squared minus y to the fourth, y between negative 2 and 2. We're going around the y-axis. Okay, so we have let's see. Theta is measured from the y-axis. So let's see, this is x, this is going to be z, and this is f of x. So x is f of x cosine theta. Z is f of x sine theta, and y is y. So our parametric equations are going to be f of x cosine theta, y is y, and z is a maple. Let's see. Okay, let's go to maple. And let's just use T for theta. Y and I don't know, let's let y, y's from negative 2 to 2, t's from 0 to 2 pi, and we get a picture that looks like this. So this allows us to graph surfaces. When we change them to parametric, we can graph the surfaces that's the result of the rotation. That makes it a lot easier. Okay, let's look at 32. So the point R1, 1, 1 goes to the vector 1, 1, 1, which is the point in the plane. So what we're trying to do is we're trying to find an equation in the tangent plane. So this gives us the point is in the plane. Now we need two vectors that are also in the plane, and if it's tangent, then we have RU and RV. So RU is 2U, 0V, and at the point 1, 1, that's 2, 0, 1. And RV now we find the normal vector. By taking the determinant. And so we have a point and plane, and we have the normal vector, so the tangent plane equation is going to be negative 2x minus 1 minus 2y minus 1 plus 4z minus 1 equals 0. Okay. 36. This looks like a plane.